Okay, let's welcome the Victor from the Latrobe University to give a talk about extending the coalgebra formalism for the construction of integrable and superintegrable system. Let's welcome Victor.
Yes. Okay. Thank you, Theo. First, I'd just like to thank the rest of my organizers for organizing this talk. It's my first time in this, and special thanks to CU and Douglas. It seemed they put a lot of work into making this all possible. So my name is Victor, and I'll just talk about the research I'm doing with my supervisors, Ian and Peter. And especially given the previous talk on the geometry aspect, might be a little more introductory in terms of the background, but hopefully this would be an interesting talk. So I guess firstly, just yeah, with the background. So what do these terms mean? So I'll just start. So just with the Poisson algebra. So this one it's most generally. So it when yeah, Poisson algebra is just an associative algebra. So a vector space with multiplication over F endowed with a bracket, which satisfies these first two properties. So it's anti-commutative and satisfies the Jacobi identity. So it's a Lie algebra, and also it satisfies this additional Leibniz property. So, or you can just see that the adjoint action acts as a derivation on the algebra itself. So, um, for our future construction, so they will almost always rely on this kind of special proposition on the case of when your algebra is a space of functions on n coordinates. So we can define the Poisson bracket as on the coordinates themselves, and if they satisfy these three properties, so and commutative and Jacobi identity in particular, then we can extend this to define a bracket on a space of all functions in terms of the sum with these commutators. And then this would become a Poisson algebra and in fact be commutative. So in particular, then you can see that the original Leibniz property can be sort of refined into what I'd call an analytic property. So instead of just effectively the product rule of the Leibniz property becomes sort of analogous to a chain rule, and you can see that these are sort of equivalent. And just in general, when we work in function spaces, this will be our basically our new third property, our analytic property. So if you know the brackets on k functions, G1 to Gk with h, then you can find the bracket with any smooth function of these original k functions. All right, so two relatively straightforward examples, I'd say, is that firstly is if you have your little g being a just a finite dimensional Lie algebra, so trivially it satisfies those first two properties and commutative and Jacobi identity because it is does its bracket is just Lie bracket. Then applying the previous proposition extends this bracket into the Poisson bracket on the entire space of smooth functions of the dual space of G. So we're just being the space of functions on the generators Xi. So for this bracket, so I guess you call the internal bracket of the generators maps into the vector space itself. And then for a slightly more interesting example, which is actually going to be the focus later on, is that if again we let the Poisson algebra be the smooth functions on just a vector space, real vector space with coordinates x1 to xn, and A be any real n by n skew symmetric matrix. So its transpose is just makes it is negative values, yet negative. Then, if we define the bracket of xi to xj just be this quadratic term, xj multiplied by the value in A, then this you can actually show, and this is kind of a separate simple algebraic test. It satisfies the Jacobi identity and also anti-commutativity. So this extends to a Poisson bracket on the space of smooth functions. So this isn't precisely a quadratic Poisson algebra, but we would just call this a quadratic Poisson algebra with constant parameters. And this is especially relevant near the end when I talk about, starting from some of these for up to some n and then extending it to larger n. Okay, so for future, um, we will no longer be working with like the more general cases where we have the just the Leibniz properties. So this would be for things like talk about with enveloping algebras. We will only be considering function spaces. So henceforth, big P is the algebra with the smooth functions on finite dimensional vector space as its underlying vector space and the bracket to be constructed or discovered. Okay, so just again, very quick recap, hopefully, just to lay down material. Unlike with the previous yesterday's talks, this is not very much focused on the geometric aspect. So the when we consider a Hamiltonian dynamical system, this is we're just working in the Euclidean space. So it's just any dynamical system where the time where the time evolution is just determined by a bracket with this any function h Hamiltonian. So in particular, again, the simplest case possible is with the classical mechanics. So if you have a system with n degrees of freedom, then there are two n canonical variables, position and momenta, and the Hamilton's equation is determined the time evolution. So with these two, and this can become like, the term Hamiltonian is being very overloaded here, but this does become a Hamiltonian dynamical system with this Hamiltonian H, provided that we define the Poisson bracket on the space to be one of the simplest possible. You just make it so that the brackets are always zero with the when it's same P or same Q, and then and they're also equal to zero. I forgot to mention this when I and J are different. And then for PI, well, actually, yeah, it's just should be a J. So PIQJ is just the Kronecker delta. So this is like in a certain sense the inspiration for our discussions on like array brackets, but they will almost always be a little more involved, the Poisson algebra itself, than this case. Okay, so again, just a little more background. So if you have a dynamical system with a Hamiltonian H, then an integral of motion or first integral is an function I, which commutes with the Hamiltonian. So in particular, its time evolution is just constant. It's zero, so it's constant. Or it's a conserved quantity. And then this is of interest, of course. We all know that that's because it's invariant under time evolution, then orbits within it are going to be invariant as well, and this restricts the evolution that it has, and up to a point where you might even be able to determine the orbits precisely just by knowing them, if you have enough. So this is a property of the dynamical system. For the algebra itself, so a Casimir invariant is some function which commutes with all of the xi's. So by the analytic property, this means that this C is in the center of our Poisson algebra. And this is something that, again, is distinguished with the geometric cases that we talked about yesterday, because in many of those cases, we consider an even dimensional space with no Casimir. Whereas in contrast for this talk, Casimirs are actually like the star of our considerations. Okay, so in talk about integrability, again, is slightly different from before. So I will mention some of like signposts, like definitions, but our aim, or is my aim, and our aim is more general, is just to construct systems with large numbers of integrals. So even when you have so something in between the formal definitions of what we'll talk about later with integrability and superintegrability, is there's a general idea that more integrals are good unless they are linearly dependent, because even just having more, they still partition your or you still restrict your orbits. They still give you information on your dynamical system. But still, what are some signposts? So a integral system, it's super integrable of rank k if there are n minus k functionally independent integrals, so which just means that there is no smooth function of these integrals equaling zero, or as one of the yesterday's talks mentioned, um, if the gradients are linearly independent. So if they're function dependent and then k of which commute with all of them, then they are super integrable of rank k. And it's maximally superintegrable if there are n minus one functionally independent integrals. So this is your maximum case, because if this is just the case where you just have um, all your integrals here will by definition they commute with the Hamiltonian. So n minus one plus one is an n. And then it's Liouville integrable if there are half n minus r commuting function-independent non-Casimir integrals. So you recall that the previous talks that integral was with there being half of n. So this is the case when you have an even dimensional space and then no integrals. These will match, but they will no longer match if n is odd, and then you will have integrals. Okay, so now so from, remember our previous talk with the coalgebra formalism. So the aim is, constructing these systems. Well, the coalgebra formalism is a way to extend a known system with a Casimir and into greater ones. So for background, so they're based on some tensor product space. So just have a regular tensor product of vector spaces, and you can define your Poisson bracket in this canonical way. And then a Poisson coalgebra is just a pair, P delta, where P is a Poisson algebra, then delta is a coproduct. So that's a Poisson map from P into the tensor space of P of itself that is co-associative. So it satisfies this property. And as maps from P into the triple. And all this really says effectively is that you can think of this delta basically iterating on itself, because there is now no ambiguity on which of these terms it is acting on. So, and before there's kind of also maybe an important point to mention, which is that since we are trying to focus on working with function spaces, and now with this tensor product, we have tensor products of function spaces, how can we return to our function, just our original function space? And we do it with this kind of formalism. So we just, for the first case, or where with just two product element copies being multiplied, we can identify the first copy with is x1, and then the second copy with this x2. And this extends into a injective homomorphism from this thing into just the smooth functions of all of these variables here, so which we call P2. So this is non-surjective, of course, because there is some twisting allowed in the P2, which will not necessarily be allowed in just a tensor product space. But this is, in many situations, nicer to work with, although there are some situations where the tensor product formalism is nicer to work with as well. And just as a space, P2 can define just by extending the brackets, where the brackets on when it's on the same space is just the original one, and then it's just zero. So if you just forget about the function, just think about this as just the vector spaces. This is a Lie direct sum of vector spaces. And we can repeat this process just as we can repeat this process later on, mentioned with making into M tensor products, we can construct a homomorphism from this into just M copies of our original vector space. Okay, so just we mentioned here with the extension. So the extension is just a matter of iteration. So again, we can, if we have an n, then we can apply, well, sorry, we can have a base case of just the delta 2. Well, if we are given a delta n, we can apply this just by fixing everything and then applying delta 2 to the first thing. Although note that, again, since it's co-associative, we can put delta 2 in any of these and it will all be the same. So then this will be, a co-product, but more important for us, this is going to be a Poisson map into this larger space. Although with our alternate formalism, it's going to be into the codomain is going to be the Pn, this space of n copies of our original vector space. Now, fine. So with the actual coproduct formalism itself, so we have a Poisson bracket, Hamiltonian, Casimir, and then an iterated coproduct. Now, the larger space that we're interested in is defined by the this Hn, so the coproduct n times of the Hamiltonian, although it could be any function of the coproduct of the variables. We just pick this as a standard case and we consider the co-products of our Casimirs. Now, generally, in this space, the original Hamiltonian is not an integral, and the original Casimir is not it does not, sorry, and the deformed, called the deformed Casimir is no longer a Casimir. So, however, we can sort of think of these deformations as losing information. And is it possible for a Casimir to retain like some level of compatibility? And the answer is yes. And this is the causal formalism, the construction of new integrals, because in this space, the because we well basically because we have these co-products are Poisson maps, the co-product of the variables, they actually commute with the co-product of the Casimirs as long as this k is less than or equal to n. So these ck's, they're all integrals. And then in fact, if you have two of these, then their co-product is equal to 0. So we know that these integrals pairwise commute. So if you go back to our dynamical system, this quadratic formalism gives us, well, one extra integral, just the deformation of the original Hamiltonian, and then n minus 1 integrals, and n Casimirs, where these Casimirs, they're just the did I find it for okay, yes, I did define this here. So if you can just shift the Casimirs into any variable because these copies here, they're basically all just copies of our original space P. So our Casimirs in any of these labels will remain Casimirs. So this gives us effectively two n integrals. So what is this is a very well-known kind of idea. I think there's the talk afterwards that also talks about coalgebra formalism. So my interest is in the specific case of the from Ballesteros, so with Ian and Peter, of the Lotka-Volterra system. So a Lotka-Volterra system of a dimension n is a dynamical system defined by this formula. So this term here is our homogeneous part, and this is an inhomogeneous part. So if we take n to be equal to 3 and A not being skew symmetric, then this system is Hamiltonian. So we can take our Poisson, which is be smooth functions on 3 coordinates, and then brackets defined by extending these. So in particular, if we go all the way back here, we can see that that bracket is the quadratic Poisson algebra with constant parameters if our A skew symmetric. So you see that this and these match, and where these terms are arbitrary. Now, this system actually has a Hamiltonian defined by summing the linear terms of the xi, which gives us the homogeneous part, and then log terms, which gives us the inhomogeneous part. And here I'll actually quickly note that with the that this does not live inside the polynomial algebra. There are other places where just to find Casimirs and like the spaces should be a polynomial, and then also this Casimir is not polynomial either. So this might be called a generalized Casimir, but here we just call them Casimirs. So we have our our base, our Poisson algebra P, a Hamiltonian H, and then this is the Casimir C. So last need is coproduct, and Ballesteros finds this by considering the Poisson structure on a related space. So you can define coproducts like these. This is in the tensor part of formalism, and then in our function-based formalism, we can write like this, which has the advantage that it's straightforward to extend this to the coproduct on the entire space by just applying function composition. So f is a function of x, y, and z, and delta 2 dot y, z. So these are all just large functions. We can just compose these. So, and as before, we can iterate to construct our coproduct discharges Shav and X to define a higher coproduct on delta 3. Although I'll note that this is a place where the tensor product formalism is a little more natural. Here you could just write as x, x, x. But when you apply the iteration with this formalism, you actually have to do some relabeling because now this x, if you do it on left, for example, this the term that results has to be wedged in between the x1 and x3. So we have the one iteration, and this we can proceed inductively to get iteration for any n. So with these forms. Okay, so conclusion. So if you have then from early on, we talked about having constructing of n and n plus n minus 1 plus 1, so 2n integrals. So in particular, since we have a 3D space, this is a 3n dimensional space, and then with 2n integrals. So for example, two nice cases are, again, ignore the typo, with just one deformation. So we're going to have two Casimirs, and then two integrals. And then with the next deformation, H3, we're going to have three integrals and then two Casimirs. Three Casimirs and three integrals. And these are all function dependent. So in particular, they're integrable, but again, less focus on integral itself. We're trying to constructing more integrals. And while in this form, our next section, well, actually, lets us get more out of this H3 case. So our research, with Ian and Peter. So first part is how to construct more. It's with this shift operator. So you can define this by just taking the copy living in J and just moving it up one. And you can do this to the variable. And then, of course, if you do to the variables, and as long as you're not having any overflow, as long as you don't have any variables of n, you can define this on any function by just composing this with f. So in particular, as long as this if your original function lives in Pn minus k, you can compose this at most n minus 1 times and still give and the result is still well defined. So then we can define a shifted Casimir to be this construction here. So you apply the coproduct M. This is going to have terms living in the space 1 to space M, and then composing this with shifting k minus 1 times. So, okay, yeah, again, and this should be M, and then this k is less than this. And then in particular, this absorbs our previous cases, because if we take M tribute to 1, this is just the original trivial shifts on the Casimir. And then if you take the lower value 1, this is just the mth coproduct. So in fact, these are also integrals. So the act of shifting these doesn't actually, because n is larger than everything here, it turns out that you preserve this property of we still have more integrals. And then a nice condition for the commutativity is just that either the this is this intersection is empty, where so it's obviously zero because there are no sort of matching terms. All the xyz live in different spaces, or if there's complete inclusion. So a plus b minus one, the terms living here are contained inside the ones here, or vice versa. So there are, so these, whoops, sorry, moving up. So if you have space um, and consider the mth coproduct, you can shift this by n minus n plus one times. So this number of shifted Casimirs, they grow with the triangular number, oops, the triangular number on n. So we have n plus one on two integrals as shifted Casimirs plus the Hamiltonian. Now, obviously, this is way too many. You can't have more than just and integrals in general. So these can't all be function dependent. And in fact, at most 3n minus 2 of these are. However, again, in terms of a goal, we are constructing more. So in particular, in our 3D case, we had three Casimirs and three additional integrals. This shifted Casimir formalism produces one more, and this is functionally independent, although we they don't commute with all of them. So this condition is broken when considered C22 and C21, and in fact, they don't commute anymore. So the we no longer have a set of pairwise commuting integrals, but we do have a slightly larger set of integrals. Okay, the second part, oh my gosh, I should rush a little bit, is just constructing Casimirs for more general quadratic algebras. So we consider for the case of n equals 3, well, what happens if we consider larger n's? So it's just two simple properties. One is that by skew symmetry of Aij, the evenness of the dimension, it will be the same as the evenness of the Casimirs. So we know when an n is even, we have the normal sense where you just don't have a Casimir, but when n is odd, there's always going to be at least one. And then in terms of solving for them, it's a straightforward exercise because, in fact, the Casimirs, they all have this nice form, and the exponents of them are just elements of the null space of A. So we just solve for null space of A, we get the Casimirs. So for n equals 3, this is going to be our matrix of parameters, and there's this one Casimir if A is not trivial. For n equals 4, look at this, and then it's if this value E1, which is a determinant squared, is 0, then you have two Casimirs, otherwise you have none. So if you have two, and for example, A is not 0, then the two independent Casimirs will look like this. And then for n equals 5, looking at this, and then it's going to have, it can have 1, 3, or 5 Casimirs, 5 if it's trivial, and then it has three Casimirs when there's the three sort of control terms. They're all 0 because you can apply re row reduction to get into something like this, where this is also a skew symmetric matrix. So for example, if we fix A equal to 0, not non-zero, then it reduces to this. So if this is all 0, then we're going to have just these three Casimirs. And if one of them 0, we have only one Casimir looking like this. Okay. And the last part, the main part, which, oh my gosh, it's the last bit, is extending the 3D case. So if you start with our original Poisson coalgebra, then we consider, hey, what if we add another variable? So we consider the vector space of just with functions with this W, and we extend the algebra structure. So the XYZs, their bracket is the same as before, and then we just make them, constant coefficients, and we just extend the Hamilton a little bit. So what can we make this a Poisson? Can we construct our coalgebra formalism with this? Well, if we try to extend it, we're going to have a maps of these three are as before, and this W is just an arbitrary function that we want to solve for. And if we assume to be Poisson map, then we have three first order PDEs. So for example, if we just set these equal to 1, then we can solve in Maple and get that the coproduct is an arbitrary function of 5 variables. Okay, and if and then fixing so we get the able to apply coalgebra formulas on this larger space, I will just rush through it so that we don't get too late, and then we can just repeat this process. Oh yes, do you mind if I just have take 1 minute just to? Okay, actually, it's okay. Yeah, so okay, I'll just finish now. So we have sort of this diagram, and then there's some technical considerations that I should probably rush it because it's already 11:30. Okay, thank you.
Okay, thank you for Victor's talking. Any question?